All right, so just to kind of let you know where we are, this is the home stretch. I've got one more lecture on LDA on Thursday, and then today I'm going to talk about something called parameter servers. Then Tuesday, we'll hear some presentations, short presentations by the students in the 805 research, the people who are doing projects. So that'll be what we do on Tuesday. So if you're in 605, you should come. There may be like a really lightweight quiz that will just basically make sure that you did, attend. So like one year, I asked a question on a quiz about what kind of animal was used to like illustrate one of the speaker's points, because they used gophers, and I figured everybody would remember the gophers if they were there. So you should come and see what your classmates are doing, and then Thursday will be the final. Okay, so this lecture is about parameter servers. And the assignment that's coming out now is about parameter servers. So I should remind everyone you can drop your lowest assignment grade. Some people, if they sort of get to this point, have done all the assignments and done okay, they just drop the last one. But of course, not everybody wants to do that. So this is a slightly lighter weight assignment than most of the other ones. We're giving you a little bit more help, but it should be an interesting assignment. So parameter servers. So I actually kind of feel weird giving this talk. Parameter servers have been a big deal at CMU for the past several years rather. So Alex Smola came from Yahoo Research, did a lot of consulting work with Google, sort of starting kind of around the time that he got here. And this is an architecture that he talked a lot about and did a lot of analysis of. And later, Eric Zing and his research group picked up the project and kind of took it in a slightly different direction. So there have been a couple of big groups at CMU over the last several years that are building machine learning systems based on these ideas. So we've always had a talk on parameter servers in this class, but usually it was given by either Eric or Alex or one of their advanced PhD students. So it's possible I'm not even the biggest expert on parameter servers in this room, since one of our TAs is also working on that project. But I'll tell you what I know about them. And the idea is basically pretty straightforward. But first, let me just scare you a little bit with some hard-looking math, okay, just to kind of wake everyone up. Earlier this semester, we spent a bit of time analyzing the perceptron algorithm. It would make a bounded number of mistakes, which you could, upper bound based on properties of the data set, basically how well separated it was, and what was the complexity of the data in the sense of the radius around the origin that the points fit into. And then I talked kind of briefly about how that analysis could be extended. And I didn't kind of wade through the math, but I talked about this really cool paper from a few years back by John Langford and Alex Smola and a few other folks. What they did was they proposed the following model. So this is basically stochastic gradient descent, all right? But it's a slight variant. It's called delayed stochastic gradient descent. So let's kind of just step through what this is. We've got some space of examples, all right? We've got a learning rate, which changes over time. And we've got this thing called a delay, all right? What we do is the following, okay? We're going to loop through the data, maybe many times, but we're going to basically go through on each time step t. What I'm going to do is the following, okay? I've got some function, some loss function that I'm optimizing, right? So I classify the example, I incur my loss, all right? I compute the gradient of that loss with respect to the last example, All right, so this is all kind of what I do in kind of normal stochastic gradient descent. And then I do an update. So the update sort of has two parts. The first one is I take an ordinary gradient step, okay? Except not quite an ordinary gradient step. Instead of using the current gradient, I'm using the gradient with respect to t time units ago. So I'm using an old kind of stale gradient, and I'm going in that direction anyway. All right, so I take that gradient step, and then all this stuff right here, it's basically you're sort of taking that, you're projecting it into some set of valid classifiers X that you're allowed. So maybe this is a regularization step or something like that. And that's sort of my the next point, my next parameter set. So X here is not a data point, but it's a parameter set. You're looking at the gradient, and you're taking a step, and then you're projecting. And the key thing is you're using this delayed version of the gradient. Sort of a special case of this. And the evaluation we use is you basically look at, well, how well did you do in this process? So what's the actual total loss that you incurred as you are going through each of these examples in this online dynamic fashion, right? And how does that loss compare to the best loss you could have chosen in that set? So this is basically the best classifier, or maybe one that has zero error in separable data case. And this is the loss that you actually incurred. And the loss might be 0, 1, so in which case we'd just be talking about mistakes, but it might be something more general. The loss might be something like log loss if you're doing stochastic gradient descent. So this is what we're measuring regret, basically. What's the penalty for doing things in this online way? All right. And it turns out you can make some pretty strong statements. So these are basically complicated properties of the data. Like this this F here is sort of like the space that the examples are, or actually the classifiers are sitting in. So it's something about how diverse that set of classifiers is. This is something about how quickly the loss changes. But the real thing is the regret you get is sort of the square root of t multiplied by tau. All right, and tau is the delay. So the more delay you have, the more loss you're going to get. All right, but you can bound it. You can tolerate a certain amount of loss. Right, and then there's some other kind of like slightly more complicated things. So we can get something which basically is order tau squared with a log t factor and times root t. So there are other cases where we can make these bounds a little bit tighter, but basically this sort of works. So it's kind of the short story is if you do this sort of delayed learning where you're taking a gradient step, but that gradient step is based on a slightly old set of parameters, probably things will be okay. You might learn a little bit more slowly in terms of the number of examples you need to look at, but there could be well be a win because, of course, if you allow yourself to use old parameter values, then that opens the door for all sorts of clever ways of parallelizing things. So we can basically have several SGD learners kind of zooming through the data, updating parameters as quickly as they can, and we probably want to keep them more or less synchronized. Okay, we don't want to let them completely diverge and never look at never share information about their parameters, but we can have them sort of be somewhat loosely synchronized. So this is one of the key ideas behind parameter servers. So this is sort of the same math that's kind of going to come up to justify this approach. So parameter server is basically a machine learning architecture. All right, we can kind of think of this as sort of three different levels. We've got these machine learning algorithms, we've got abstractions, we build those on, right? And then we have systems that implement those abstractions, right? So to take an example of this, right, we've got these layers. If we look at data flow systems, we've got concrete systems like a Hadoop or Spark, right? And then for graph systems, we've got concrete systems like Pregol or GraphLab. This third abstraction we're going to be talking about today is parameter servers. And there are several variants of the parameter server. The one you guys are going to be using is Boson, so it's the latest Petuum variant. So the algorithms that are sort of suited to these things vary, right? So naive Bayes and Rocchio are easy things to put on Hadoop. Things like PageRank and personalized PageRank, shortest path, various sorts of graph algorithms fit really nicely in a Pregel architecture. And these are actually really good for a lot of machine learning tasks as well. So a lot of the kind of standard things like stochastic gradient descent and so on work really nicely in these parameter server models. Okay, so the abstractions that we use on top of this, right, would be things like, here, things like guinea pig or pig, right? Here, the abstraction we use are these user-defined functions that run on each vertex. And here, the abstraction we're going to talk about is the parameter server abstraction. All right. Okay, so what is a parameter server? Well, it's basically kind of what it sounds like. So what we do is we put the parameters of a machine learning system. So in the easy non-distributed case, the simple thing to do is just put all those parameters in memory and stream through the data somehow. Okay. If we want to do this in parallel, sometimes we don't have enough space in memory for all the parameters. Of course, if we did have enough space for all the parameters, we still couldn't easily use a whole bunch of machines in a cluster to do processing because they'd have the parameters in different memory spaces, right? So here the idea is the parameters are stored in a distributed database, okay, that's accessible through the network, okay? As I said, a lot of the academic work on this goes back 5 or 6 years. Alex Mola is one of the kind of early guys. Eric Zing is someone that's kind of been pushing this idea very heavily over the last few years. So this is an idea that's kind of been out for a while. There are a lot of things you can do with it. So this is a graph from a recent paper on Peduum, Eric's parameter server model. And these are different, so these pink things are all topic models, LDA type things. These blue things are convolutional neural networks, okay? And these are matrix factorization problems. These are other deep networks. And these guys are all things that have been implemented on a parameter server framework. So there's lots of things you can do with a parameter server, okay? So here's the basic idea. We take the model parameters and we store them on a network of machines. So we basically have two subnetworks. These might actually be the same machines, right? So we might have the same machines doing work serving parameters and also, doing data processing work. But conceptually, these are different. These can be different. These different boxes. So we've got a bunch of parameter servers. And we have a bunch of workers. Okay, these guys are basically responsible for storing the model parameters and getting them to the workers as quickly as possible. All right, so this is basically implementing a sort of distributed shared memory. All right, so the simplest way of accessing these is just a key value interface. So you give it some ID for the parameter and you get back the parameter value. If you give it an ID it's never seen before, it will tell you some default value, usually 0. So what these things look like, what the parameter space looks like to you is basically one big sparse vector. And there are a couple of extensions which have been added. So as I said, there's several different parameter server systems. So one extension might be, for example, to allow you to access parameter not by one key, but by a combination of keys, maybe 2 keys, which means you're accessing items in a sparse matrix rather than a sparse array or sparse vector. Okay, so sometimes I'll have sort of multiple channels, and each channel you can kind of think of as sort of the name for a different parameter space. So that might be useful if, for example, you're using the same parameter server cluster to, let's say, train a new version of the parameters for tomorrow, and also serve yesterday's parameters to clients that are using those for, I don't know, ad placement or something like that. Another kind of cool extension, the parameter servers, the server machines are basically tasked with the goal of getting the parameters to the workers as soon as possible. It's often helpful if the workers can give the servers a little bit of information about when they're likely to really need fresh values or when they've made a change that might be important. So a common extension is, in addition to just sort of have a key value method for retrieving the current value of a parameter or updating a current value, you might have a push-pull interface where you give it, say, some subset of the parameters and say, okay, I'm going to need all the parameters that, that correspond to weights of features in this, this collection of documents I just pulled down. Okay, so I need to get all the values of all these parameters, and I'd like the most recent one now. And then you might do some updates, and you might say, okay, I want to now sort of advertise the fact that I've made changes, and I'd like to make sure everybody else gets these as soon as possible. So that would be a push and a pull, or a pull and then a push. So when you do that, there's a question of what the semantics for these things are. So normally when you do a pull, you're asking for the most recent values of the parameters. When you do a push, you're saying, I'd like to advertise these and make them available to everybody. But there's a question of what happens after you've made that call. So for example, when I say I want to pull in some new set of parameter values, the system might be, the semantics of that according to the system might be, it's like, okay, well, I'm going to make sure that everybody else that's accessing these parameters is already done. Everybody has already pushed everything they have to say about these parameters before I let you get your new parameter values, right? Or you might not, right? So there are a bunch of extensions where basically the push pulls might block or they might not block, and it basically depends to some extent on how far behind the other worker machines are running. So that this is basically implementing some notion of this maximal delay. So we saw in the math it's kind of okay to let multiple machine learning processes, in the case of stochastic gradient descent, diverge a little bit. It's okay for them to work on slightly different values of the parameters. But you say you pay a penalty as the parameter values get staler and staler. So you can put some parameter in here, tau, which tells you how stale you're willing to let the parameters get. And that can be implemented in terms of these push-pulls. All right, so that's all abstract. So these slides, which have been distributed to me, these were Oryx slides from last year. I have these nice animations. So here's kind of a picture of what happens. So typically, when you're using a parameter server, you parallelize over the data. So typically, each worker will have a different chart of the data, okay? And then each parameter server is going to have a different chart, set of parameters that it actually locally hosts. Sometimes these overlap and they get synchronized back and forth behind the scenes. But the simple case is there's a different set of parameters for each server. Then as the workers do their computation, they request these parameters and they update these parameters, okay? And after that computation is over, the parameters will be updated in the server. So we have different parts of the model on different servers. Parameter servers are also extremely robust. Very robust platform. You can use redundant. I didn't do it here because to decide how to partition the model. The model is based on the operation of the system, right? So there'll be some different sets of parameters that are accessed by most systems, but you sort of explicitly determine that. Okay. I think I found a bug in PowerPoint. I'm still not going to send them the bug, though. I'm sorry. Fix your own code. All right. So, so let's move on. All right, so the simplest API is basically sort of a get set. So we can get the key and that returns a value, the parameter value, okay? Or you can add some delta to that key. So you can increment or decrement it by some amount, all right? So this is sort of the simplest level of abstraction, all right? So just kind of to quickly, since they have these cool animations, to quickly contrast this with the way Hadoop works. So in Hadoop, you might also try and do a similar sort of thing. You might shard your training data, all right? Then you might do some sort of map reduce process, which gives you the deltas over those trained parameters, all right? And then you would reshard those. So let's say you were doing, naive Bayes or SGD or something like that. You'd have a whole bunch of different parameters, and those would be in different shards, okay? Then you'd aggregate those, right, and do it again and again, right? So this is iterative parameter mixing. We looked at this in the McDonald paper earlier this year. So the downside of doing this is every time you're doing this, you're loading the same data, okay? So the data is not really cached, okay? So there's a lot of read, and then when you're saving the output, you're also saving a lot of output. So you're saving the new parameter values each time. You're writing them to disk, and it's kind of a tragic inefficiency because, of course, you don't even really care about these intermediate values. That's really, there's only point in storing that is kind of for checkpointing. Okay, so let's look at the underlying execution model. So the one that you guys will be working with is called stale synchronous parallel. All right. So here's the basic idea. We've got a bunch of examples. We've got a bunch of workers that are accessing those. The workers are all conceptually accessing the same model parameters. Okay. So what's the execution semantics that we want here? Well, we could just say, well, whenever I get a key, I'll get the most recent value of that key, and whenever I add, I'll update, and that will go to anybody else that asks for it. The problem is the networks are a little bit too slow to make that efficient, okay? So if you remember the numbers we talked about earlier in class, the network is much, much slower than a local memory access, right? So we need to do something to kind of speed things up. So what we're going to do in the parameter server model is basically a combination of local caching and then kind of delayed updates to the synchronized model. All right. So the baseline one baseline that we could use for this is to basically have one version of the data that's synchronized everywhere. So everybody does some processing locally. These guys are the workers with their own little shard of data. Okay. After they've done some processing, they make some changes, but not to the whole model, just to a small part of it. So they're making some sparse changes to this, all right? Then at some point, they push that data back, all right? And everybody blocks until it all gets put on the server, okay? And then you start over again, all right? So that's one possibility, okay? Where you basically do a pull, you do some processing, and then you do a push, and then another pull. So that basically means things are completely synchronized in this setting. And this is a lot like the iterative parameter mixing. The only thing that's different is the data here can be stored locally, so you're not necessarily reading it each time. But the parameters are all distributed, not by Hadoop, but by this parameter server. All right. Another possibility, as you can imagine, is just doing everything completely asynchronously. All right. So I've got 3 worker machines here. Okay. They do some iteration over the data. So in the synchronous case, we basically wait for everybody to finish. Okay, we do some communication. So we synchronize the caches, get all that data collected, mix the parameters, and redistribute them. Then we have another process. So here we basically have to wait till the slowest guy finishes before he can start computing, right? So we've got a little bit of wastage, and we could get rid of that if we just said, well, what I'm going to do is I'll just sort of start communicating as soon as I can, and I'll iterate as much as I can. That is something that's potentially more efficient, okay? The downside of this is that, here I've drawn it so this machine kind of goes through 2 iterations. Around the same time this machine goes in 2 iterations. But it could very well be, since these machines are looping over the same data, there's one machine that's just systematically a little bit slower. So it's going to fall further and further and further behind. And the one that has sort of the easiest data to work through is going to get further and further and further ahead. So the problem with asynchronous communication, this would be the parameter server idea, right? Where basically they're communicating and they're all communicating with the parameter server. Problem with doing it purely asynchronously is you can have machines sort of fall arbitrarily behind or get arbitrarily far ahead. And it's very hard to say anything formally about what happens in that sort of setting. Okay. So that's why we look at this model here where we have sort of a bounded delay. And in the parameter server setting, this is called bounded asynchronous. And the semantics are pretty simple. There's this global clock time, okay? So this is something that kind of lives in the parameter server. The workers can get something. When they get something, it can be out of date, but it can't be too stale. All right, whatever the real time is, it can't be older than t minus tau. All right, so you're willing to let, things fall sort of like tau clock cycles behind, but not any further than that. If you ask for a parameter and the version that's in the parameter server is older than that, okay, so there's some pending update from the last tau time units, then you block. Okay, so you don't actually get it until the other processes that are using it catch up to that extent. So this controls how stale things are going to get. The other name for this, besides bounded asynchronous, is stale synchronous parallel, or SSP. Okay. This is actually kind of an interesting model. So if we let the staleness be 0, that basically means that nothing can fall behind at all. Okay, so then you run into so that's basically the same as sort of the fully synchronous model. Okay, so staleness of 0 is basically means you're synchronizing completely. Everything sort of gets the same parameters at the end of each clock cycle. Another possibility is to let the staleness parameter be infinite. Okay, so then you basically never block, right? Because when you're getting a parameter, you're basically saying, well, I'll take anything up to t minus infinity, right? No matter how old it is, I'll just take it, whatever. Okay, so then it's fully asynchronous, you never block. And then you lose any theoretical guarantees and things can get sort of arbitrarily far behind. But often a small amount of staleness will eliminate a lot of kind of like wasted time. So this turns out to be a pretty useful model. So here's an example. So this is basically fully synchronous. So you've got a delay of 0, right? And this is time. And this is for running LDA, latent Dirichlet allocation, on a cluster of 32 machines. Okay. What you basically see is that if you make everything synchronous, then you spend a lot of time waiting. All right. So you're spending much more time waiting for the last process than you are computing, right? So as you increase the staleness, so the compute time doesn't get any better, but the wait time sort of drops, all right? And somewhere around, wait time, a staleness of 24 or 32, you're getting to the point where the wait time is no longer dominating your compute time. So ideally, you'd like to get it down to 0, but really, if the wait time is, half your compute time, you've kind of gotten most of the way towards efficient. So a suitable delay can give you a big speed up. Of course, it comes with a cost, right? So you're not converging as fast. So how quickly do you get to a good model? So here the differences aren't quite as dramatic. So this is still this 0. So that's or bulk synchronous. So it's fully synchronous. And you converge. That's fine. And this is wall clock time. The asynchronous version actually converges faster theoretically for this problem, this LDA problem. It's not guaranteed to, but in this case it does. And then staleness with, a value of 32 here, which was sort of around the kind of sweet spot, sort of gets a significantly better model in less time. So that's kind of the basic idea. Are there any questions? Jane, you have any comments? Have I missed anything? Have I got anything wrong so far? He's like, uh-oh. All right. So this is kind of the general idea. Let's go a little bit beyond this. So in this model, you basically specify very little. You basically sort of say when the clock ends. And you say how stale you want things to go. So you can look at using sort of explicit pushes and pulls to manage the communication a little bit better, okay? Empirically, when you're doing this, in bulk synchronous, there's a barrier where computation just stalls, all right? When you're using SSP, there's less time where it stalls, okay? Only if certain, previous syncs didn't complete will you stall, okay? But you still may not be using the network to its best capability. So in particular, you don't really know you're going to need a parameter until you start pulling for it. You could, in fact, if you could sort of give the server a little bit of a heads up and say, I'm going to need this parameter pretty soon, you could maybe get that parameter to you more quickly. You also might be able to structure the parameter space a little bit better. So in the case I looked at, I just said, well, we'll just put the parameters, randomly, we'll scatter them across the different servers, maybe replicate a little bit and synchronize behind the scenes. But conceptually, the parameters are just on different servers. And when you ask for something, that request sort of bounces around until you figure out who actually has the most recent value, and that kind of gets to you. But maybe you can do better than that if you kind of know how you want to structure the computation. So the kind of solution to that is basically just add a little bit more stuff to the API to give the system a little bit more hints. So here's one common thing you want to do. One common thing you want to do is you want to basically take the model that you're serving and partition it into different slices. So we're going to talk about some examples of this further out. An example of a regularized regression problem. But you can think of lots of cases where you might want to partition things. So for example, maybe if what you were doing is doing naive Bayes or stochastic gradient descent, and you had two sets of parameters. Maybe you had global parameter values, global accessible words, and user-specific words. So you did this little trick that Langford did. So you might want to partition those into two different spaces. Or maybe you were classifying documents and you had the links in the documents and you had the words in the documents. You might have two workers for each of those things. And of course, they're accessing different parameters. So it might be helpful to know that, right? And have the requests go more directly to the right place. And have the delays be kind of localized to that particular set of parameters, okay? So one possibility is you might want to segregate the model parameters. Another case you might want to do this is maybe in deep learning. You might want to have level 1 here and level 2 here. The other thing you might want to do, so remember when we were talking about the graph-based models. So in the graph-based models, one thing that helps is to do things asynchronously and to basically not do updates for parts of the graph that have already converged or very close to convergence. So you might decide that some parameters are kind of less important to update, right? So you might let the staleness vary on a parameter by parameter basis, okay? Let's talk about how to get these ideas into an API. And to do that, I'm going to first talk a little bit about what sorts of problems we're solving. So the typical kind of thing we're looking at is a machine learning algorithm. Typically, this iterates over some data. All right. So we've got some set of parameters. So this is parameters at time t. This is parameters at time t minus 1, obviously. Okay. So A is my set of parameters. Okay. D is the data. So at some point, we're going to compute the loss on the data, and more specifically, we'll compute the gradient of that loss. Okay. So this delta, sub L here is basically the gradient, of my current parameters on the data. Okay. And what I typically do in each time step is I compute that gradient. All right. And I use that to update the parameters. Okay. So this f function is an update. It's taking the old parameter values and the new ones, and the gradient, and then updating it. So usually f would be some, plus equals, minus equals sort of operation on a vector, right? And then this would be whatever your loss function's gradient is. Okay. So there are a couple of ways that this gets broken down. So the common one that we've talked about so far is basically doing it in parallel by sharding the data. Okay. So we can shard the data. So we're doing the same sort of update. Okay. Again, we've got a gradient of the parameters with respect to some shard of the data here. Okay. All right. I dropped a little super L here, or rather Eric did in his paper that I'm splicing these things from. So this is the local gradient on a particular shard. Okay. And then these get combined almost always by adding them. Okay, or something like, a weighted sum, right? So this is what we do when we basically shard the data, okay? We've got these local gradients, we combine them somehow, all right, and then we do an update, okay? So, the reason we can add things is we're assuming this is some sort of, log likelihood type model, all right? And that the data here is IID, okay? But this is a pretty common case, all right? The other possibility is we basically sort of split things up by the feature set. So we've somehow taken the model and parallelized the model. So we're essentially sharding the set of features we have to look at each point. Okay. So what does that look like here? So we've got something a little bit similar. So I'm simplifying this by just ignoring the data here, right? But we've got some shard of the features. Okay. And this, in the example we'll look at, this actually changes over time. So we've got the pth set of features, okay, at time t minus 1. So we choose some subset of those, right? And then we compute the gradient of that, okay? So this is a gradient with respect to some subset of the features, okay? And we do that for each of these, and we combine them somehow, right? Usually not by addition, all right? And then we do our update, okay? So what we basically need here is we need something that's going to choose which parameters to think about for each to distribute to in each shard at each time step. All right. So that would be sort of a model parallel sort of approach. Okay. Or if you like, it's data parallel versus feature parallel. So this suggests I have the following kind of interface. So I've got a push and pull. Okay. The push talks about a particular range. So S varies is some subset of the variables. So it's some range of parameters you're going to, or some set of parameters you're going to use. Okay. So when you do a push, you're basically telling this something about which keys have been changed. Okay. When you do a pull, you want to get again, you want to get fresh values for some subset of variables. Okay. We're also gonna have something which decides on these different subsets of variables. And the way this is set up in Pedalum is that these blue functions run on the scheduler side, all right? And this is what happens on the worker side. So the worker side basically pushes things, and the scheduler will pull things. So it's going to wait for these, pushed operations to happen. It's going to pull parameters back and then aggregate them somehow, okay? And it will also make these scheduling decisions, all right? And I guess now we've got a fair bit of work going on in the process in the scheduler process, okay? So before the workers did the work and the scheduler basically was just distributing keys around, now there are other things that it does. So in addition to sort of exchanging parameters, there's also this control information. And there actually can be these complex scheduling routines, potentially complex scheduling routines that choose a different set of to use. That also happens in the parameter, but fortunately it can happen asynchronously. So it doesn't necessarily slow down the worker machines, it just means you sort of have to throw more computers at the problem. So this is the API that you end up with. So there's a schedule routine, okay? What it typically does is it gets some parameters, it might change them, okay? And then it will return something that will select a subset of variables, okay? And that what gets returned when you call schedule, all right? When you do a push, you'll get the name of the worker ID, and so that's sort of the name of the shard. We'll get the set of variables we want to use for that shard, okay? And we can do the same sort of things. We can get parameters. We can update them, okay? We can make changes, okay? And when we're done, we're going to basically send something back, which will indicate what the changes have been, all right? I don't know why this suddenly turned blue. There's nothing I can really do about it, I don't think. I don't know if that's any better. All right. And then when you do a pull, this happens on the schedule function, okay? So essentially what happens is you wait for these pushes to finish, okay? So you're getting information back from the worker machines, you do some sort of aggregation, all right? And then you update the parameters. So this is actually, I mean, in my mind, this is very similar to what happens in the signal collect framework, okay? So when you do schedule, you're essentially defining a graph, right? So the kind of, the computation elements are the nodes in the graph, all right? So this is basically deciding who gets to push what to where, okay? So it's sort of the connectivity, okay? So when the workers push parameters, it's like essentially doing a signal operation, all right? When the scheduler does a pull and aggregation, that's essentially like a collect operation. All right, so it has a lot of the same feel as signal collect, although obviously the differences there are a lot of differences at the detail level. Okay, so a couple of examples. So the simple one is where we just shard the data. Let's just kind of take a look at what this would look like. So this is an example from Eric's paper. It's the one on there's actually 3 papers on the website. One is by Alex Smola, it's the oldest one. One is by Eric, and it's a relatively recent one. And there's another one by Eric, which seemed a little bit more introductory. But this is from the most recent one of Eric's papers. So the problem we're looking at here is distance metric learning, which I haven't really talked about, but it's a pretty simple idea. So in distance metric learning, rather than classification, so in classification, someone gives you an example, X, and you say what the label is, +1 or -1, let's say. All right, here someone gives you 2 examples and you say, are they similar or not similar? Okay, so are they nearby or not nearby? All right, so our model for what's nearby is we're basically going to do this. We're basically going to take each example, x1 and x2, and we'll scale them by doing a linear transformation. So I multiply by this matrix L, all right? And then I can just look at, Euclidean distance or squared Euclidean distance and threshold that. So what we want to do is we want the things that are marked as similar to be as close as possible. So we want to have that be minimal. With the things that are dissimilar, we want that number to be large. All right, so let's say I want it to be mostly towards 1. That would be sort of like one plausible answer, right? So that would lead to this sort of loss function. So where we've got a summation over the similar pairs. And here I'm using x and y instead of x1 and x2. I find that a little confusing, but this is the formula they use. All right, so similar pairs xy and dissimilar pairs d. All right, so here we're basically sort of trying to minimize the the distance between these, and here we're sort of trying to push it up towards at least 1. Okay. So, so this is our loss function. And we can just solve this by doing stochastic gradient descent. All right, we can compute the gradient of this. And we end up with this sort of process. Okay. So we're going to get a local copy of the parameters by doing a get. Okay, and this is using, let's say, stale synchronous parallel, right? So it's going to get this, these parameters, and if necessary, it'll sort of wait until for other guys to catch up. You also could only just get the keys you need, although it's not really indicated in this little pseudocode. All right, and then I'm going to basically sort of look at aggregate the changes in a mini batch. Okay, so I've got a bunch of examples. So I have some local data that I have cached out here. This data construct is my local data shard, and we'll take one similar pair and one dissimilar pair, and then we'll do the gradient step. Okay, and we aggregate all these. All right, and now we're going to increment these. Okay, all right. So this is basically what the pseudocode looks like for a data parallel stochastic gradient descent type thing. And here we're just using like sort of a particular version of that because we're looking at pairs instead of examples. To aggregate these things, we don't have to do anything. So this is just basically sort of like we're using the default of basically not doing any aggregation. And to schedule things, again, we don't do anything. So we'll just let everybody access all the parameters. Okay. And in the paper, there's some results to show that this works. So this blue line is 1 machine. This purple line is 4 machines. So there's definitely kind of a speed up. If you look at how much time it gets to take to get the same objective function, there's a speed up of maybe 3 or 4. Okay. So here's the complicated example. So this one is model parallel. So this is a case where what we're doing is we're sharding instances instead. Okay. So I allocated a bit of time to talk about this because we haven't really talked so far in this class about doing this sort of parallel machine learning. So most of what we talked about is machine learning where what you parallelize is the data. So you split the data, shard the data between different workers, and you sort of try and make that work. But there is an alternative. It's less commonly used, but there's some cases where it does work nicely, and this is one of them. So this is a technique called the lasso, or L1 regularized regression. So we talked about this earlier. So when we were talking about stochastic gradient descent, logistic regression, we've got some loss function on the data. So this is log conditional likelihood, right? And then to avoid overfitting, we basically regularize this. Okay, so we look at log conditional likelihood, and we penalize that by some factor or some fudge factor, and we just penalize it by the square of the sum of the square of the weights, which is basically the L2 norm of the data. Okay, so that's a really nice function to work with. When I differentiate this, I just get sort of like a linear update, and it seems to work pretty well in practice. Another one is instead of using like the square here, you can use an absolute value. Okay, so if I use an absolute value, I'm also penalizing weights that get really large or really small. There's one point where that's not continuous, right? At 0, the absolute value function is not continuous, right? So there's a little bit of a break in the gradient, but you can sort of deal with that. You can basically just sort of clip the gradient when it changes signs. And then what we're basically doing is we're using this penalty term, so the sum of the absolute values. All right. So this turns out to have surprisingly different properties. Okay. So here's the L2, here's the L1. so this is penalizing weights based on the square, okay, that blue line. This is penalizing weights based on the absolute value, which is these red lines, okay? And if we kind of zoom in here, we can sort of see what happens as you get really close to 0. That's when these things start to change dramatically, okay? So I mean, since if we're like, you know, a ways out here, we're looking at pretty large values, there'll be some difference between how much penalty we get, but it's not that dramatic a difference. What really happens where things get really different is kind of close to 0. Okay, so very close to 0, this quadratic curve really, really flattens out. So the gradient is basically linear in the size of the parameter. So as you get closer to 0, you basically stop moving, okay? So if you have a parameter that's pretty worthless, it's going to end up with a pretty small weight, okay? But you know, as that weight gets smaller and smaller, the changes you make to that weight are also going to get smaller and smaller. So it's going to get kind of mired down here and just sort of get stuck, all right? Whereas if you look at the L1 loss, so the gradient there is basically sort of a constant. So the gradient of that is always going to be just whatever the slope of this line is, wherever you are on it. So as it gets close to 0, it's not going to slow down, right? It'll keep moving at exactly the same speed, right? And you know, sort of depending how, you know, what you do when you get kind of close to the end. So you could actually sort of, you know, if your steps are a little bit too small, you sort of keep bouncing back, and if your steps are large, you'll sort of keep bouncing back and forth between positive and negative, right? You know, effectively what ends up happening in many kind of L1 regularized systems is at some point you basically just sort of clip the gradient and say, well, I'm going to just stop moving at 0, right? So to summarize, here you get a really shallow gradient near 0. Here the gradient near 0 is still pretty steep, okay? So what this regularizer is going to do is it's going to push parameters not towards 0, but actually to 0, all right? So you'll get a bunch of parameter values that are actually 0, so you end up with a sparse classifier that basically just doesn't look at a bunch of parameters at the end of the day. So that's nice practically in a lot of ways. So, so for example, if some of those features were hard to compute, then you might end up with a classifier that you didn't need to compute all the features for. So you could just, you know, save a little bit of time at classification. It also makes the classifiers easier to store and transmit and so on, and easier to understand. So this sort of L1 regularization is kind of a nice technique. All right. So that's sort of the first step. So the second new thing I'm going to talk to you about is coordinate descent, okay? So we all kind of know and love stochastic gradient descent. We just go over each example. So we have a little loop here, an outer loop, and we take an example in each pass through the data in each epoch. All right, we compute the gradient of the regularized loss for that example. So just locally on this one little tiny piece of the data, we compute gradient, and then we move all the parameters in that direction. All right, so that's stochastic gradient descent. All right, there's another optimization technique which I haven't really talked about called coordinate descent. All right, so here the idea is the following. What I'm going to do is, again, I'm going to go through each epoch, you know, several epochs. But in each epoch, what I'm going to do is not look at things example by example, but I'll look at them coordinate by coordinate or feature by feature. So I'm going to look at each feature. All right, I'll compute the gradient of the regularized loss for that feature, assuming everything else is fixed. Okay, so I'll say, well, if I just wanted to change this one feature, how would I change it? Okay. So you look at the gradient of the regularized loss for that feature, and then you move that feature, okay? So often you move that feature a long ways. You might probably do a line search and sort of figure out what that feature's optimal value is, okay? And then you go to the next feature and you set it, and so on and so forth, okay? So this is called coordinate descent. You know, kind of the picture is well, I guess we'll get to a picture of that pretty soon. But this is coordinate descent. This also has some nice properties. So what this basically means is you're sort of doing an optimization step for one feature, and sometimes you can do that for a really big feature space efficiently. So there are times when coordinate descent is a really nice thing to be able to use. And there is actually a stochastic version of it. So in ordinary coordinate descent, you cycle through each parameter one by one. And stochastic coordinate descent, you basically pick a random parameter and then you move it the same way. Okay. So that's another optimization method. It's got theoretical bounds. It's competitive in some situations. And there's also a cool way of parallelizing it. Okay. So if we're going to parallelize SGD, what we do is we take a bunch of examples and we do a gradient we do a gradient computation for each of those examples independently, and then we aggregate those gradients and move. Okay, right? Here's another way of doing it. So here, what we're going to do is we're going to, instead of choosing one coordinate at random, we'll choose a bunch of coordinates, again at random, but in parallel. Okay. So for each of these coordinates, we're going to compute the gradient of the regularized loss for that gradient. So maybe I've got, for that feature, for that coordinate, so maybe I've got 10 coordinates here. I'm going to compute 10 gradients, keeping all the other ones fixed. All right, and then I'll make a move in that direction. Okay, so that's the basic idea. Here's kind of the pseudocode for it. What I'm basically going to do is I'm going to pick a random subset of weights. Okay, and then in parallel, I'll just figure out what the gradient is, and I'll move that direction. Okay, all right. So here's a little picture that kind of shows what you're doing here. So what kind of happens in coordinate descent is the following. So in normal coordinate descent, you compute the gradient of one. So let's say you're here, right? You'll compute the gradient of one feature, right? So we've got two features here, x and y, right? So we'll compute the gradient of that one feature, keeping the other one fixed, and we would say move there, okay? Right? Then we compute a gradient of the other feature, keeping that one fixed, and we move there, right? Then we might make another move, like maybe over here, and another move over there, okay? So in kind of standard coordinate descent, you'd be sort of like cutting a little kind of staircase, all right angles kind of thing through the space, eventually reaching the max, okay? So in parallel coordinate descent, you take two steps, compute them independently, then you just add them up and you go there, okay? So in this situation, that works great, okay? You're going to get really close to the optimal, all right? Here's another situation. So this is the gradient for the x value, and in real life, and if I was doing this, just using coordinate descent, I take a step here. I say, well, where do I have to go? It's like, okay, I'll move another one. So maybe I'll move it up here. Then I'll compute the gradient of that. And I'll make another move back this way. And then I'll compute that. So I'll be like taking a little kind of like etch-a-sketch sort of path, all right angles, that'll eventually get me to the middle. All right. And I know at each move I'm making reducing loss for one of the coordinates. So eventually things will get better. But what happens here is when I take this coordinate and this coordinate and I add them up, I end up with something that might take me in the wrong direction. So here's kind of the right direction. Here it's kind of the wrong direction. And it's the right direction here because these gradients are more or less independent, right? These two features aren't very well correlated, all right? But here these features are really correlated. So moving this guy is going to affect the y coordinate. Moving in the y coordinate is going to affect the x coordinate. All right. So because these two features are really highly correlated, it doesn't make sense to take their gradient separately and then just add them up. All right. And in fact, in the worst case, when you do this parallel coordinate descent, which is sometimes called shotgun, when you do this parallel coordinate descent, you might converge a lot more slowly, or you might even diverge. Okay. So when we implement this, here's the basic idea. What we're going to do is we will pick a set of parameters stochastically, okay, but we're also going to impose a couple of preferences on this. So we're going to prefer parameter values that are large, because once things get small, they're mostly converged, so we can sort of, we're going to basically sort of try and not schedule those updates at all. All right, we're also going to try sets of parameters that are independent. All right, so so here's the code, right? So all the action here is basically in the scheduling, all right? So when I pull, basically I get a whole bunch of things that have been computed by my workers, and each one of these are, individual coordinate updates, all right? And I basically go ahead and aggregate these things in the normal way and update my parameters. Okay, so this is basically just doing a summation of these vectors. Okay, so here's where all the kind of interesting work is, where I choose which set of k values to look at each time. Okay, so first thing what I'm going to do is I'm going to look at some sort of priority. So I'll look at, so beta j is the value of the jth parameter. Okay, he's using beta for the parameter values instead of like w for weight. All right, so we're basically going to scale that up. So we're going to add eta so that everything gets some probability of being choiced, and then I'll add the square of the parameter value, and then we normalize that to make a distribution, and then we randomly draw L prime things. Okay, so we randomly draw L prime things, but kind of focusing on the large parameters. Okay. Then I do a filter. Okay, so I'm going to take each of those things. I'll look at the correlation of those. All right, and if they're uncorrelated, then I will I'll pass them through. Otherwise, I'll discard them. And then finally, do a parallel step over the ones that kind of pass the correlation check. All right, and each time it's going to be a different random set of things. There'll be a set of random things that are not well correlated. Okay, and there'll be a set of things that still have large values. Okay. So then the code in the middle is basically just computing the partial derivative here. Okay, so here what we're going to do is we've got so here we've got the set of values that have been returned by the scheduler, okay? What we're doing here, this is actually confused. Oh, I see. So this is, yeah, okay. Oh, I see. So this is actually data add, I'm sorry, I take this back a little bit. This is data add model parallel, which is actually often the case, okay? So, so here we're actually going to take the pth shard of the data, and we'll compute the derivatives of each of the partials for each of these parameter values with respect to that subset of the data. So this worker just has a slice of the data sub p, okay? And that's why what we have here is, what we end up here is a vector of partial values, and then in this step here, we're aggregating these things, okay? So we're summing up these computations from the different workers, okay? Okay. All right. So so this is an example of a more complex parallelization. We're parallelizing both by instances and by features. All right. And kind of the short story here is that sort of seems to work. So this is sort of the old parallel shotgun, and this is the lasso. And I apologize because I'm actually not done. Let me get my last little slide deck here. Oh. Okay. So here's the last and most relevant case study for you guys. Okay. So this is topic modeling with LDA. All right. So you guys kind of remember how this works. So we've got one set of multinomials. So for each topic, we've got a multinomial, which is a distribution of words given that topic. Okay, so this is a big set of parameters. Okay, this is basically sort of like k different naive Bayes vectors over the whole vocabulary. This is going to get maintained by the parameter server. Okay, and then there's basically the documents. Okay, so each worker node is going to have a subset of documents. All right, and the documents, what we basically know is we know the word, so that's xi in this notation, the latent topic for that, and we have a distribution for that document of what topics are prevalent in that document. All right, so the way we do this is with Gibbs sampling. All right, so for each of the words, the non-stop words in a document, we've got some latent variable. Okay, and those are all drawn from some document-specific topic distribution. All right. So I also have a word topic distribution. So there's a whole bunch of documents, and then we have a whole bunch of words. And what I'm basically going to go through is cycle through these things. I'll pick a latent assignment for this word brains based on that topic distribution. All right, then I'll pick a latent topic for head based on that distribution, and so on. Okay. All right. So to partition the model, all right, we can partition the words just randomly. Okay, so we'll just have a different subset of word IDs on different shards of the parameter server, different pieces for the parameter server. Okay, and then we'll have different subsets of documents on the worker nodes. Okay, so when I ask for word-specific probabilities for each topic, I'll be able to get those and use that for the update. Okay. And when I have finished choosing a new topic, then of course that's going to update these the overall counts. So so the parameters that I really want to store here, I said distributions, but what we're storing is like a global count of how many times each topic is each word. How many times each word has been assigned to each topic. Okay. So we'll be adding to those. All right. Okay. And of course, it's a little more complicated because there'll be a cache of the parameters that are used locally in each one of these things. Okay. So here's the sort of result we should be able to see. Okay. So there are a couple of cases here. So there's stale synchronous parallel, which I've talked about. There's something called eager stale synchronous parallel, which basically means you call a push to indicate that it's okay to kind of start transferring values. Okay. And here's some other comparisons. So this is using light LDA, which is a more complicated version of what you're dealing with. So we'll talk a little bit later on about what that's all about. But again, this is sort of the kind of results that you get. So this is using 6,000 machines in a parameter server, right, versus 1,000 machines. So on a big data set, we can actually get sort of an improvement in how quickly we can get improvements. We can learn an accurate model. So that's basically the last little step. So these are different LDA experiments, and I guess the point of these is just to show you that this is kind of an extremely scalable approach to distributing the computation. Okay. So I'm going to stop now. I'll stick around for another 10 minutes or so if people have questions. And I will see you guys on Thursday when we'll talk about kind of more tricks of the trade for speeding up LDA.